Good afternoon. So today we'll learn two more ways to figure out whether a series with positive terms converges or not. And there is a big discussion with these properties, whether we should cover them and, to what depth, let's say, let's put it this way, to what extent. And in particular, the comparison test is a little bit not controversial, but it's debatable how much instructors should insist on it. I think it's an important concept that helps in understanding the whole idea of convergence of series. It will help you essentially guessing under quotation marks. I mean, like figuring out just by looking at the terms to a great extent whether the series will converge before you even try to prove it. And that's an important skill, I think. And so it's important to have a good idea just by looking at the general series with familiar terms. It's important to have a good idea whether that will converge or not. And then you will worry about how you prove it. And I think the comparison test reinforces this skill. On the other hand, the comparison test can be replaced by the limit comparison test in most situations. And the limit comparison test is more straightforward. The comparison test can be tricky to apply if it's applicable at all. And if you don't really understand well what it states, it's a source of mistakes or confusions. So I'm going to go over the comparison test, but I will only require you to use it in straightforward cases when it's obvious how it can be applied. It's based on an inequality, as you'll see immediately. So without further ado, let's state what the comparison test implies. So the comparison test, and by the way, both are comparison tests in the sense that you have a series and then you have another series, presumably easier to analyze, or a series for which you know whether it's convergent or not. And because of that comparison, you'll conclude what happens to the original series. So suppose we have two series, an, summation of an, and summation of bn, series with positive terms. And for all practical purposes, imagine that this summation is actually known. It's the comparison term, so to speak, of the comparison series. And this is really the question, right? This is the one that you're trying to figure out whether it's convergent or not. And then basically you compare it with another one for which you actually know whether it's convergent or not. And so the test basically has two parts. It simply says that if the summation of bn is convergent, and pay attention here to the direction of the inequality, and an less than or equal to bn for all n, then you can conclude that summation of an is convergent. So essentially, if your an in your series is less than bn, that comes from another series for which you know is convergent, then you can conclude an is convergent. So less than finite, less than convergent is convergent. And the second part of the theorem is if the summation of bn, right, from 1 to infinity, sometimes I omit to say from 1 to infinity if it's obvious from the context. So if bn, summation of bn is divergent, and the inequality is in the other direction, an greater than bn for all n, then your series is divergent. So the source of mistakes here is that if the inequality is in the incorrect direction, the test says nothing. So you cannot conclude anything. And intuitively, let's say an intuitive trick, think in terms like this: less than finite is finite. greater than infinite is infinite, right? So that's what the test essentially says, these two parts. On the other hand, greater than finite, there's nothing we can conclude. Greater than finite could be finite, another number greater than that, or infinite. By the same token, less than infinite, there's nothing we can conclude. It could be a finite number, it could be an infinite number. These two statements provide nothing. So I'm crossing them out so that it's clear on your notes that there's nothing you can conclude from that, as you will see with some examples that I'm gonna work with right now. So let's see how this comparison test applies in obvious cases. So let's suppose you have summation from 1 to infinity, square root of n over n third plus 6. So the skill that you need to have here is basically to kind of guess whether this will actually converge or not. And the idea is basically to look at the dominating terms. That's the overall hint in problems like this. If I'm looking at the powers of n, powers of the top and the bottom, so I have n to the 1/2, n to the third, and think also that you learned previously something about the p-series, the fact that they actually converge if p is greater than 1. And then stands the reason that this is kind of close to a p-series with p greater than 1, simply because you have such a bigger exponent on the bottom compared to the top one. In fact, if you compare the exponents of the leading terms, square root of n and n third, it'll be like 3 to the minus 1/2, right? If you were to simplify those dominating terms. So it's still something greater than 1, which suggests convergence. So how would you prove convergence with the comparison test? Well, all you have to do is to come up with a sequence. So you take the sequence that forms the original series, and you take a sequence that will give you a convergent series, but that's greater than this. So you need to find a series whose sequence term in the summation is greater than what you have here, and yet still convergent. And usually the trick works if you simply take the new series involving only the leading terms. So if I drop the 6, that's not like a universal rule, but if I drop the 6 from the denominator, that means I'm decreasing the denominator, and by decreasing the denominator, I'm increasing the overall fraction. Now if I actually simplify this, n to the 1/2 from the top, you're left with 1 over 3 to the n to the 3 minus 1/2. That gives me 1 over n to the power 5 over 2. So now I have a clear instance of the first part of the limit comparison, of the comparison test. Because this is a p-series, right? So the summation of 1 over n to the 5 over 2 is a p-series with p greater than 1. This is going to be convergent. And because this is less than this, then I can conclude by the comparison test that my original series converges. So in the theorem, this stands for an, this stands for bn. Your given series, the sequence that forms your given series, is less than another sequence which forms a convergent series. So basically, this is the type of problems when we're going to use this test, when these types of inequalities are quite obvious, right? So I'm looking at root n over n third plus 6. That's awfully close to this, which is convergent. Not only close to that, but less than that. So I'm going to have less than convergent, therefore convergent. Here's on the flip side an example that deals with the second part of the theorem. Let's say I have the summation from 1 to infinity of root n plus 1 over n. That's awfully close to root n over n, which is essentially 1 over root n, which is 1 over n to the 1/2. So I'm guessing this will be divergent, but to be able to use the divergence, the comparison test for divergence, the second part, I'm gonna have to come up with a quantity less than root n plus 1 over n and still divergent. Does it happen to be less than root n over n? Yes, indeed, because the dropping the 1 from the radical decreases the numerator. So you make the numerator smaller, which makes the overall fraction smaller. So the inequality is in the correct, look on the top here, it's in the correct direction. Because on the right hand side, I end up with a divergent series. So because summation of 1 over n to the 1/2 is divergent, since it's a p series with p less than 1, then I can conclude the original is divergent. So we're going to move on with other examples, obviously, on the next pages. But again, before we do that, pause for a moment and maybe reread again the theorem. We need the proper inequality in each case. Less than convergent to conclude divergence, less than convergence to conclude convergence, greater than divergent to conclude divergence. If anything, if either of these two conditions breaks down, then the test will fail, as I'll show you with some examples. So stay tuned. All right, so sometimes the comparison test is very tricky to apply, and I'm going to point out a wrong way to go about it. If you don't pay attention, you can apply it in the wrong way, which also motivates the second part of the lecture, namely the limit comparison test, which is easier to apply in many cases. So let's look at the following example. Summation from 1 to infinity of n plus 3 over n squared plus 5. And let's say we try the comparison test in the following way. Let's say we may suspect that it's, let's say we suspect it's, what I was going to say, convergent. So let's look at an inequality in the direction less than or equal to. So suppose you decide to drop the 5 on the bottom, which if you do that, it will increase the value of the fraction, right? Because you make the denominator smaller, so you make the fraction bigger. Does that help via comparison test? Well, it will help only if the summation of what you obtain on the right hand side is convergent, because the direction of the inequality can only be used if you suspect convergence, so therefore you need something less than something else convergent. But is it convergent? Well, let's break this down into n over n squared plus 3 over n squared. This is a summation of 1 over n, because n over n squared is 1 over n, plus the summation of 3 over n squared. Now this is convergent, but this is divergent. So remember, you add infinity to a finite number, this will be divergent. So does not work. That doesn't mean we know the answer. It's still an open question at this point. Is this series converges or not? All I just showed you is that this try with this series, n plus 3 over n squared, doesn't give me a way to apply the comparison test. I can't conclude anything because the inequality gives me something less than a series which is divergent, so that does not help. Again, remember, don't try to add to the theorem when there's nothing to add. So far we know nothing about the original series. This test series will not work for the comparison test. And see, this can be tricky because, for example, if you keep on suspecting it's convergent, you'll try to have different versions of Bn, different inequalities. And if you try the obvious ones, maybe it's time to think about whether it is divergent. And in fact, with what I'm going to show you with the limit comparison test, you'll tell quickly in this case that this is actually going to be divergent. But I just want to point out that if we limit ourselves just to the comparison test, and if we don't know anything else about the series, it can be a tedious process that may lead to nowhere if we keep on trying the comparison test in the wrong direction. Okay, so then let's say I suspect that is divergent, in fact. So that flips the question right now. Like if I take the original sequence, if I suspect divergence, then I need to figure out a series that is less than the original one, which will give me something divergent. All right, so let's drop the constant first of all on the top. So if I drop the 3 on the top, that'll give me a lower quantity because I decrease the denominator. And let's see if I can drop that 5 but still keep the same direction of the inequality. So if I increase the denominator, I can still further lower the fraction. And here you also can think about n over n squared. Again, you always look at the dominating terms because that gives you an estimation of whether it's convergent or divergent. So I can simply replace 5, for example, with 2n squared. And by the way, this will be true, I mean this direction inequality, especially if n is greater than or equal to 5. Now remember, the summation doesn't matter if it starts from 1, from 2, from 3. I mean, if the inequality holds for all n's after a certain value of n, the overall conclusion is still the same, convergent or divergent. So the first couple of terms don't change the nature of the series. So anyway, this is going to be now 1 over 2n if I simplify by n. And indeed, the summation of 1 over 2n, if you pull the 1 over 2 outside, this is divergent. So therefore, your original series is divergent as well. So the summation from 5 to infinity, if you have to be picky, but it'd be the same from 1 to infinity, n plus 3 over n squared plus 5 is divergent. All right, so I think that's enough for the comparison test. If we have quick inequalities that I can produce in the correct direction, we will use that. If not, let's do something slightly more powerful and more straightforward to actually apply. That's basically related to this. I mean, but you know, when you apply it, it's much more straightforward. You don't have to come up with these inequalities. So let's state the so-called limit comparison test. Also known as LCT, I mean abbreviated by LCT. So the limit comparison test again uses two series, the given one and the one you try to compare it with. So suppose summation of an, summation of bn are series with positive terms. From now on, you feel free to not specify the beginning of the series. Because in terms of conversion, that doesn't matter. For power series, it matters because, not for the convergence, but it matters for the computation of that power series. Because remember, in that case, we have a mean to compute the sum. And so in that case, you have to be careful whether it starts from 1 or from some other number. But just for convergence, it doesn't matter. So suppose these are series with positive terms, and suppose that the limit as n goes to infinity of an over bn is equal to c, where c is finite and positive. So positive constant. Then the limit comparison test states that both series converge or diverge. So As Bn is, so is An. Summation of Bn is convergent, summation of An is convergent. If summation of Bn is divergent, summation of An is divergent. So all you have to do is to compute this limit and see if C is finite and positive, then the nature of both series is the same. Now the trick is, and usually it's not a complicated trick, the trick is to find Bn in such a way that the limit is indeed finite. Because if it's infinite, then this test doesn't work. You need to pick the second series in such a way that the limit is finite and positive. And it will be positive because you have positive terms. I mean, shouldn't be zero, right? But otherwise it's a positive number. So let's actually move on the second page, on next page for examples. All right, so let's do an example involving polynomials, which these are one of the classical examples that deal with the limit comparison test. So suppose I have to figure out the summation from 1 to infinity, the convergence or divergence of the series, let's say 3n squared plus n over 5 n to the power 4 plus 1. All right, so here's an important remark here. Very important, because it will save you a lot of trouble if you remember this. When you have quantities like this, like rational fractions or similar to rational fractions, in which it's kind of like infinity over infinity if you look at the limit as n goes to infinity, then the series to choose to compare it with, because remember in the theorem this will be an, the question is, how shall I choose the summation of Bn so that I can apply the limit comparison test, so that I can get that limit to be a constant greater than 0. And the answer is to always pick Bn made of the dominating terms of an, right, of the given series. That's nearly always works. So just come up with a series involving just the dominating terms. So for example, and by the way, that 3 and 5 actually doesn't matter. You could just pick n squared and n fourth. It doesn't hurt to pick 3 and 5. So I mean, if it's confusing without them, you could feel free to do that. So in fact, let's just do that. So suppose that I'm choosing Bn to be 3n squared over 5n fourth, which if I simplify n squared, that's going to be 3 over 5 times 1 over n squared. And with experience, you can tell right at this moment that is going to be convergent. From this point on, it's just a matter of showing that you know how to use the comparison test. But you're guaranteed, if you choose Bn in such a manner, to obtain a finite limit positive. So therefore, both series converge or diverge. So let's go slowly with the limit comparison test. So once you pick Bn like this, so therefore I'm going to pick summation from 1 to infinity of 3 over 5, 1 over n squared, for which I know it's convergent because it's 3 over 5 times a p series with p greater than 1. Right, so we know that much about my pick. The only thing I have to show is that the limit of an over bn is a positive number. So I'm going to put 3n squared plus n over 5n fourth plus 1 divided by 3 over 5n squared. Okay, and then let's simplify this a little bit. Times 5n squared over 3, and we're gonna have to distribute 5n squared, so that's 15n to the power 4 plus 5n third divided by 15n to the power 4 plus 3. Normally in calculus 1 you would show that this, because this is an infinity over infinity limit, and you have to write it in terms of limit that can be computed directly, so you can pass the limit. So you divide by n fourth in both on both sides, so that's 15 plus 5 n third over n fourth, which is 5 over n over 15 plus 3 over n fourth. And then you can pass the limit 15 plus 0 over 15 plus 0, which is 1. No need for this in this class. I'm just mentioning this because in Calculus 1 you did that. Just use that theorem I mentioned, or the property that I mentioned before. In the case over infinity, the limit is given by the limit of the dominating terms. When you have rational fractions like this, which in this case is going to be 1, right? If you simplify 15 and 4. So your C is equal to 1, which is greater than 0. So therefore, by the limit comparison test, the original series converges. Okay, so summation of Bn that you picked converges. Limit comparison test gave you the limit, which is equal to 1. Positive, doesn't have to be equal to 1. Any number, positive will do. So therefore, the original series is just like the one that we picked, convergent in this case. So let's do another similar example. So suppose I have summation from 1 to infinity. Let's say 5 square root of n divided by 2n squared plus 3. You should probably pause the video at this moment and ask yourself, just by looking at the ratio of the dominating terms, ask yourself whether this is convergent or divergent. And in fact, if you get the hang of it, let's do another quick example, kind of similar to this. So try to do both before you continue the video. So what if I have, let's say, let's do it like that. So 3n plus 1 divided by let's see, 2n squared plus n. Yeah, so do it with the limit comparison test in both cases. All right, so assuming you just did that, let's actually check the work. Dominating terms. So you could tell quickly which one is which. Because remember, for functions like this, eventually it'll be just like the series given by the dominating terms. Summation of root n over n squared, which simplifies to, let's see, 1 over n to the 2 minus 1 half, which makes it 4 over 2 minus 1 half, 3 over 2. So this will be like a p series with p greater than 1. I could tell from the beginning that p is going to be convergent. It's just a matter of giving the argument via the limit comparison test. If I'm looking at the second example of the dominating terms, that compares to summation of 1 over n, which I know is divergent. It's just a matter again of showing the whole thing with the limit comparison test. So limit comparison test. This is your an. I'm going to pick bn, let's ignore the constants for now. You can include 5 and 2, but you don't have to. Let's pick bn to be root n over n squared, which again simplifies to 1 over n to the 3 halves. So keep that in mind. We have this bn, and now let's compute limit as an as n goes to infinity of an over bn. So I'm going to have 5 root n on the top over 2n squared plus 3 divided by root n over n squared. So that's limit, right? Limit. And now let's simplify 5 root n times n squared over root n times 2n squared plus 3. And we're gonna combine this power, so this is going to be 5, 2 plus 1 half makes it 5 over 2. and on the bottom is 2n to the 5 over, I squeezed this too much here, n 5 over 2. Yeah, I don't like that. Let's write it from the beginning here. 5n to the 5 over 2 over 2n to the 5 over 2 plus 3 square root of n. Without too much fuss, remember the limit is given by the limit of the ratio of the dominating terms. Which is 5 over 2 greater than 0. And as I said before, because the summation of Bn converges, by the limit comparison test, the original series converges as well. So make sure you understand how this works and then get used to do this quickly like that. I mean, at least the most important thing, get used to realize what the answer is even before you write down the work. Then you have to write down the work to show that you understood how the test is applicable here. Here again, Bn, like I said, is going to be made of the dominating terms, 1 over n. And then when you take the limit, as n goes to infinity, of 3n plus 1 over 2n squared plus n over 1 over n, you should end up with a positive limit. See, by choosing Bn with the dominating terms only, you're guaranteed to have a finite limit as required by the limit comparison test. So you're guaranteed essentially for the test to work. Here the limit is 3 over 2. It's positive, so, and because summation over 1 over n is divergent, so is the original series. So this will be divergent. And I think that's it for today. We're gonna have, when we're done with these tests with the criteria for convergence of series, we're gonna have basically a lesson where we just have practice. We put everything together, like, you know, here's a series, decide convergence or divergence by any means you learned. What comes after this lesson, it's gonna be another very important, well, there will be 2 important sections after this. One test that deals with series that can have negative terms, not just any negative terms, the so-called alternating negative terms, the so-called alternating series. Then we're gonna have another powerful theorem, which is the ratio and the root test and the absolute convergence of series. And then we're going to have that section which deals with, you know, like a practice section for testing series with all the theorems we learned so far. And we're going to finish the chapter with, of course, how series are applicable when you deal with functions. But we'll get to that when the time comes. So that's it for today.